Ever wondered how your social media feed knows exactly who to suggest as a new friend? Or how a bank can spot one fraudulent purchase in a million legit ones? Well, the secret is all about understanding connections. So today, we're going to pull back the curtain on the AI that makes it all happen, Graph Convolutional Networks, or GCNs. Now, that sounds super technical, right? But stick with me, because it's all built on this one really simple idea: learning from your neighbors.
I mean, think about it. We're pretty good at teaching AI to handle stuff that's nice and orderly. It can read text one word after another, or see an image as a perfect grid of pixels. But the real world? It's not like that at all. It's messy. It's this tangled web of connections: who's friends with who, which bank accounts are linked to which devices, how information spreads. So the big question is, how in the world do you get a machine to see the patterns in all that chaos?
And that's where we hit our first big idea. To make sense of all that tangled up data, the old tools just won't cut it. We need something brand new, something built specifically for networks.
So on one side, you've got your traditional data. It's all lined up in a row, like text, or in a perfect grid, like an image. Super predictable. But then you've got network data, and it's a whole different beast. It's all over the place. Some points or nodes have tons of connections, others have just one. There's no real beginning or end, and it's that chaos, that total lack of structure, that means you can't just shove it into a regular old neural network and hope for the best. It just doesn't work.
Okay, so how do we deal with that mess? Well, the solution is actually pretty brilliant, and it's called message passing. And the core idea is something we all do instinctively. You can figure out a lot about someone or something just by looking at who they hang out with.
Let's start with the most basic version of this. It's called label propagation. Picture this: you've got a huge network, and a few of the nodes are flagged as fraud. Now, in each round of this process, those fraud nodes basically whisper their status to all their immediate neighbors. They pass the message along. And as this happens over and over, that fraud label starts to spread, kind of like a rumor, and you see these suspicious clusters start to light up. It's a really simple but powerful way to smooth out information across the graph.
And the way it works is just a simple repeating loop. It's really just 3 steps. Step 1, send. Every single node shouts out its current state to its neighbors. Step 2, update. Then, each node listens to all the messages it got and uses them to update its own state. And step 3, repeat. You just do that over and over and over again. And with every single cycle, that information travels one step further out into the network.
Okay, so that's label propagation. It's a fantastic idea, but it's a little basic, right? It's only passing around one single piece of info, like a fraud tag. This is where GCNs come in. They take that exact same idea of message passing and basically give it superpowers.
All right, so here's the absolute game changer. Instead of a node just whispering one little label, a GCN has it share its entire profile. We're talking a whole package of information, what we call a feature vector. So remember how we called label propagation label smoothing? Well, you can think of a GCN as feature smoothing. It's not just sharing one tag, it's blending all the rich details of a node with all the details of its neighbors.
And this really drives the point home. With label propagation on the left, you're just passing one little thing, a single label, fraud or not fraud. But with a GCN, oh man, that user account isn't just saying, I might be fraud. It's sending its entire resume, its age, location, how often it makes transactions, maybe even data from its profile picture. Literally everything we know about it gets passed along in one big bundle.
All right, I know what you're thinking. Sending entire data profiles back and forth. That sounds way more complicated, right? Well, here's the beautiful part. The magic of it all. The entire complex-sounding operation inside every single GCN layer can be boiled down to a dead simple 2-step dance.
Ready? Here it is. Step 1, aggregate. For any node you're looking at, you just grab the feature vectors from all of its neighbors. You just collect them up and smush them together, usually by just averaging them. Simple as that. Now you have one single vector that's a summary of the whole neighborhood. Step 2, transform. You take that one summary vector you just made and you just feed it into a totally normal standard issue neural network layer. And that's it. That's the whole move.
Seriously, if you walk away with only one thing today, let it be this phrase. This is the beating heart of every GCN. First, aggregate the neighbors. Then, pass that to a standard neural net. Burn that into your brain, because we're going to see it over and over.
Okay, let's stop talking theory for a second and make this real. Because, theory is one thing, but seeing it work is what really makes it all click into place. Let's walk through a quick example, detecting content abuse.
So here's the scenario. In our graph, every single node is a tweet, and we connect two tweets with a line, an edge, if they came from the same user account or the same IP address. So we're basically linking them by shared origins.
But remember, these nodes aren't just empty dots. For every single tweet, we've analyzed its content and boiled it down to a profile. In this case, it's a 10-dimensional feature vector, and you can just think of that as a list of 10 numbers that describe the tweet. Maybe one number is for sentiment, how angry is it, another for its topic, and so on. It's like the tweet's unique digital fingerprint.
So, what's the goal? Simple. We want to classify each tweet as either abusive or not abusive. And yeah, we could try to do that just by looking at its content, its 10-number fingerprint, but the real magic of a GCN is that it lets us use both the tweet's content and its connections, the whole network context.
So, let's apply our two-step dance with a simple one-layer GCN. For any tweet we're looking at, first, it aggregates. It grabs those 10-number vectors from all its neighbors and averages them together. Then it transforms. It takes that one averaged vector and pushes it through a really simple neural net layer that turns those 10 numbers into just one number, our final abuse score.
You see that? It's our mantra again. Plain as day. We aggregated the neighbors, then we passed that summary to a standard neural net. That's it. It's the exact same two-step process we talked about, just applied to a real problem. Okay, but what if one layer isn't enough? What if we need to spot more subtle, more complex patterns? Well, just like you do in regular deep learning, we can just stack them. We can build a deeper model with a two-layer GCN.
Now, this first layer isn't trying to make the final call. Its job is different. It does the same first step. It aggregates the original 10-number vectors from its neighbors. But then, when it transforms them, it passes them through a neural net that squishes them down into a new, smarter 5-number vector. So this first layer is kind of like a smart filter. It's creating a brand new, richer fingerprint for each tweet, one that already has information about its neighborhood baked right in.
And then, layer 2 steps up to the plate. And guess what? It does the exact same two-step dance. Aggregate, then transform. But here's the key. Its input isn't the original 10-number vectors. It's the new, smarter 5-number vectors that layer 1 just created. So it aggregates those from its neighbors and passes that new summary through a final neural net to spit out our final single abuse score. Same process, just with much smarter data to work with.
And this stacking thing has a really important consequence. The number of layers you have directly controls how far a node can see across the network. With just one layer, a tweet only gets information from its direct neighbors. That's one hop. But when you add a second layer, that tweet is now getting info from its neighbors and from its neighbors' neighbors. The information has now traveled 2 hops away. Each layer expands the node's field of view.
So that simple two-step dance, aggregate and transform, that is the fundamental building block for a whole universe of incredible models called graph neural networks. But of course, the story doesn't end there.
Now, this basic model we've talked about is unbelievably powerful. But it also opens up a really interesting new question. Think about it. Our GCN treated every connection the same. But what if some connections matter more than others? Like in a fraud network, 2 accounts sharing a credit card is a way bigger red flag than them just sharing the same coffee shop Wi-Fi, right? So how do you teach the network to weigh those connections differently, to pay more attention to the really important ones? Well, that is where things get really cool. And it's a topic for another day. Thanks for diving into this with me.